So today we just want to continue with our development. Again, still on the Riemann tensor as it is for now. Yeah, in a previous presentation, we showed this. This was a commutation between the covariant derivatives for a certain vector, a covariant vector, and this was what we obtained. It's our intention in this presentation to show that this is also equal to that. Yeah, of course you can see, well, maybe something is interesting here. The same vector again by the same commutator of this, I have nu and k, and then k and nu, or kappa, all along. So we obtain something on the right hand side. We have sigma and sigma here, lambda and mu. Now if you look over on the second time, it's like the lambda moved over to the t and the sigma moved over to the Riemann tensor. And the sigma that was here moved here and the mu also came here. Well, this is the only thing that you may see obviously here that looks sort of nice anyway about that formula. But also I intend in this video to use this. We simply just stated this result last time. One of the reasons why I want to do this is also because I intend to use this expression in my proof of this. So which is why I will do this one first. So in the usual way by which we solved this problem last time, v lambda nu, comma semicolon k, v lambda here and k semicolon nu. What we can do is I can rewrite this as some sort of p lambda sub nu k minus p lambda. Okay, I think I've missed okay, well, nothing, just it's all fine. pk nu. In other words, by p lambda nu here, I mean, if you look at this expression, v lambda semicolon nu. So this is just what I mean by that. And similarly, p lambda kappa is the same thing as v lambda semicolon kappa. So it's just the usual thing. Of course, here we are going to deal with this. So I'm just going to look for some symbol here. Anything whatsoever that helps me. So something straight or just S. So I won't have to write this every time as I go. Now I'm going to say that S is the same thing as by normal covariant derivation. I'm going to say that this is the p lambda nu, the sk. I'm contracting just one index and that is on top. Let me use alpha. And this is p alpha. Nu stays where it is. Kappa comes over here. What I'm contracting, lambda comes here. And that is for the first term, minus, of course, I'm going to have two terms here, so I better prepare. Now I have the p lambda here, k, the x nu, but then again, plus, again, of course, because I am contracting a contravariant index, I'm going to use the same alpha. This is alpha. And here also, what I've got is what I've contracted, and this is lambda, which is going to be here. And the next thing, of course, yeah, sorry, I think I've made a mistake with this first expression. No. I have two things to contract. I've contracted the upper index. Yes, I've contracted the upper index. So I'm supposed to have a second term, this. So I'm going to use the same alpha here. Yes, so I'm going to leave p here. Lambda will be left where it is. Nu becomes alpha. What I'm contracting is nu. It comes over here. I'm differentiating with respect to k. So please, that was supposed to be part of it. So on this part, I'm going to continue next. Okay, I think it all can be contained here. So this is alpha. This is alpha. Now coming over here, I have here the p lambda kappa. Now again the x nu plus I'm contracting what is on top, alpha nu here, and what I'm contracting is lambda. This is alpha, kappa remain what it is. Minus I'm contracting what is up down. This is alpha, I leave the lambda on top. What I'm contracting is kappa, and I'm differentiating with respect to nu, and this is what I get. So moving on, of course I'm going to combine this. So let me just use this shorthand notation. This is going to be comma k. I'm going to have minus p lambda kappa, comma nu. Then over here I'm going to have, of course I have four terms in essence, so this is going to be plus of alpha, kappa, lambda, p nu, alpha. Yeah, okay, so let me just write this all out the way they should be. Kappa, So I have taken this first term, I'm going to take this one. I have a feeling things will be easier for me that way. Nu P alpha kappa, then this is going to be, so I'm writing this one with a plus first, plus kappa, nu alpha P lambda alpha, then minus, which is behind this. I have this alpha nu kappa P lambda alpha. And that's that about all the terms we've got for this one expression. And what we have just written out is just this, the entire expression. Of course, remember, we haven't really written them all out, because we already know, as we know, that these p's, each and every one of them, for instance, so I'm just going to write this out. Maybe let me make a partition here. I have that p lambda nu is equal to v lambda semicolon nu. And this is the same thing as the v lambda, the x nu. So, and now, because I'm contracting an upper index, so I'll bring down, instead of lambda, let me use beta this time just to make a distinction, differentiating with respect to x nu. And what I'm contracting is lambda, v, and then that is beta. So that in essence is what p lambda nu actually represents. And now, that is what I'm going to have here. Okay, now for the sake of clarity, because I'm going to be writing these two out, so I just want to make sure everything is alright. So because of that, this, the xk, or yes, the sk, I'm going to write it out, the s kappa. Then of course, p lambda nu, which happens to be the one I used here to illustrate what I'm going to do. This is the x nu, and the other one here is plus gamma. What I have over there is lambda beta nu, and then what I have here is v beta. That's for that. Now minus again, I'm going to say the x nu, then in the bracket, p lambda k, so all I've got is simply to change nu everywhere here to k, and I've got p lambda k. So this is going to be the v lambda, of course, but then the sk, that's what I've got there. And of course, I'm going to have a plus, because again, I'm contracting an upper index. This is going to be beta, but then kappa. This is going to be lambda, and this will be v beta again. And this two terms is just this first two, as you can see. Now, looking at this expression here, can we tell in any way I have here nu k, I have here k nu, alpha alpha, so it looks like we're in log. We don't even have to express or substitute what that would be in this case. These two seem to just disappear. K kappa nu and nu kappa is the same for this. And here, we have here sort of, oh well, we are not in log in this case. This continues to follow us. We must have to evaluate this explicitly. So what I've got, again, let me continue here, plus some gamma here, lambda, alpha, kappa. And then, of course, what we have here is going to be the p alpha, the x nu, then as usual, plus, since I'm contracting what is on top, I'm still going to use beta as my dummy index. So I'm going to use here beta, contracting, differentiating with respect to nu. What I'm contracting, alpha comes over p beta. Of course, that is not really what is meant. Sorry, please. I think I've just mistaken something here. When I said, just like what I've written here, p lambda nu meant for me v lambda semicolon, so I think I should be very careful here to make this. So what this should have been is p alpha nu, for instance, will definitely mean v alpha semicolon nu. So please, I'm sure that is not so much of a mistake. So that is what we should have, so that we dispense with the p's entirely. So here I'm going to have instead a v, and here also another v. And so I have here minus gamma lambda alpha nu, and again instead of p, of course, as like I've said, so following this one here is simply going to be dv. So, and I believe that should be the v alpha, the s kappa, and the s kappa being, yeah, of course, the s kappa. So what I'm going to have next is plus. Again, I'm contracting what is on top, so I'm using beta, this is kappa. What I'm contracting is alpha, so this is V beta.
And that is
It's of course obvious that these first two terms, the covariant, just ordinary derivative or partial derivatives commute. These first two terms cancel. But remember that ddsk still applies to this, and the same thing here, dds nu belongs. So actually, it's not just the first term. So very simply, I'm going to say, okay, maybe we'll take a shorthand notation. This is beta nu, and this is v here, beta, and I'm going to use comma k minus. Remembering again that ddx nu here applies to both things here. So I have here gamma lambda beta kappa. Here I have v beta. Of course, what is left for me next? So again, everything shorthand notation plus. What I've got there is gamma lambda, and here is alpha k, and this is v alpha comma, I believe that is nu, and something over there in the bracket again, I have plus. Some, this is common to both of them, I guess. That is outside, multiplying gamma, and this is alpha. And what I've got there is beta nu, I believe, v beta. V beta. And that is for this one. Now we have here with us minus gamma lambda alpha nu v alpha comma kappa minus gamma again lambda alpha nu, and I have here with me gamma alpha, and I have here gamma alpha, because I'm taking the second one, gamma alpha beta kappa, and then I have here with me v beta. Okay, so we are going to look for any possible cancellations here that might help us. Here we have a comma, but with a nu on this, and this here, nothing is cancelling really. And these two terms, we have beta beta. One of our terms here with alpha has this, and this, okay, just alpha beta, these are both dummy indices. The problem here is that lambda, for this case, has a k with an alpha, and the k here is not a dummy index, and it cannot be moved from the one with the lambda, which is also not a dummy index. So nothing cancels so far. But let's open these brackets that we have on top. So the first one over there is lambda beta nu comma kappa. Comma kappa in the sense that I'm differentiating the first one, keeping the second constant by Leibniz rule plus keep the first one constant. Beta nu, I differentiate this, so v beta comma kappa. Now minus, oh no, I think I missed, well, because it would be too late. This was supposed to be comma nu, because if you remember when this term cancelled this, I had ddx differentiating, so ddx nu is supposed to differentiate this, so I missed the nu. Yeah, there should have been a comma nu here. So I have here with me gamma lambda beta kappa comma nu. I'm keeping the second factor a constant, minus again because of the minus over here. This is lambda beta kappa v beta, but then comma nu. Again, at this point, I have plus lambda alpha kappa v comma nu alpha, plus what I have over there is lambda alpha kappa, and then I have here with me alpha beta nu, and then I have here v beta, minus lambda alpha nu v comma kappa alpha, minus gamma lambda alpha nu, and then again gamma alpha beta kappa v beta. Hopefully one or two things will cancel here. We have with us here a comma k, a differentiation with respect to sk, and I don't think we're involved with anyone. Okay, so we have something here also. And these two terms are the same because beta here is a dummy index, alpha here is a dummy index. We have comma k and lambda here and nus. So these two go, and you can see you can label them as 1 if you like, just to know what I've cancelled with what. What else again are we in log to have disappear? We need two more things to just leave us alone. Okay, now this last two. You can see here that alpha dummy indices. Now alpha is a dummy index, comma nu, and then that again. So you can label that the second set of terms that disappear. So these two again leave us alone. And now we are left here with this, that, and that. So what we have is gamma, lambda, beta, nu, comma, kappa. I'm going to leave the v beta because I guess v beta is common to all of them. Comma, nu, and that is lambda. Plus here, lambda, alpha, kappa, gamma, alpha, beta, nu, minus gamma, lambda, alpha, nu, gamma, alpha, beta, kappa. And all of these have a v beta multiplier. Of course, we can recognize this object in the bracket as I always do, r lambda beta nu k. I'm guessing, and this is going to be v beta. So S, which I'm going to write out in full, v lambda nu kappa minus v here, lambda kappa nu, kappa nu. Of course, that is what we have over there. This is the same thing as r lambda beta nu kappa v beta. I'm guessing this should be the same with what we have here. Yeah, so we have dummy index contracted with the very first index. So that is beta contracted with the very first one, nu k. Nu k in the order of the first two covariant derivatives. So again, nu k in the order of the first two derivatives. And of course, a lambda which has to follow us. So in this case, we have been able to show this expression, just like we have stated initially. And of course, that is what we have. And we intend to use this result in our next solution, which is in our proof of this. Yeah, so I'm just saying, supposing at this point that we call a certain vector, or maybe you should just look at this for a while. V mu c lambda mu. You can see that I have mu to be contracted and just one index. In essence, I can refer to this as some z lambda. And this just looks like some kind of contravariant tensor. Or it's simply just a vector because these two indices are contracted. If they were different, of course, then I would present all three on this subject. But they are not. So if it is a covariant vector, a vector, a contravariant tensor, then this formula is applicable to it. In other words, from what we have just shown, I can write that z lambda, so instead of the expression that z lambda here, kappa nu, is the same thing as, of course, r means what it is, the Riemann tensor, but then again, z beta. In other words, this will be true for this vector. I mean, because we just showed this for any arbitrary vector v lambda. Now, if that is the case, then of course we can proceed very quickly, as I show now. I'm going to take this, well, the very first term there, or the very first term, which is z lambda. So I have here with me z lambda, and that is nu k. You realize now this is the same thing as saying some v mu t lambda mu, right? It's the same thing as saying that, or this and that. So for this term, I'm going to take this again one at a time. Well, first of all, we can open up this bracket by saying that this is the same thing as v mu, that, of course, we say that the covariant derivative obey the Leibniz rule, and nu, everything still covariantly differentiated with respect to S kappa. So this is same thing as V mu. Of course, there's our mu over here. T that semicolon K, which is out there, plus V mu T lambda this semicolon K, which again means I can write this to be equal to, again by Leibniz rule, this is V, let me put that in order, K. So again I'm treating this second one here as a constant by Leibniz rule, plus I have this one here. Now I'm differentiating this by Leibniz rule. Next, I have here with me plus V mu kappa. I'm treating the second object over there as a constant, plus V mu. Now I differentiate the second object, mu kappa. Now what about the second term there, which we intend to subtract? What we have for that is some z lambda and simply an interchange of k, or nu and k, which is this. So k comes first before nu. So in other words, all I have to do is make that interchange everywhere on the right hand side. And we have what should be the corresponding expression for this. So here V mu kappa nu T lambda mu, plus this then will be V kappa mu T lambda mu, but then nu, plus V semicolon nu mu, here T lambda mu, but then kappa, plus V mu T lambda mu kappa, then nu. Of course, what we intend to do is to obtain this at this point in time minus this. So sorry, when I was talking about making interchange, I wrote exactly what will have been for the first expression. So this should have been Z kappa nu, and this will be Z kappa nu. And so what are we expecting? Of course, one could say that this too should cancel. We were saying this minus that. But remember, first of all, that it doesn't. And it's the essence of the proof that we had to go through the first time in our previous presentation, and even in this one, is to tell us that the covariant derivatives do not commute, as is the case for partial derivatives. Of course, if what I had here was some V mu, say, comma, nu, and k, of course, when this subtracts some V mu, comma, k nu, this will be 0. Of course, by that, or should I say, by V mu, comma, nu k, I mean the V mu, the 2V mu, the x nu, the xk. These commute for ordinary derivatives, but they don't in covariant derivatives. So all I'm going to do is to write out, for now, what it should simply represent. This will be minus V mu, k nu, and what is common to them is T lambda and that. What about the middle terms? First of all, again, because they don't commute, we are going to be careful, but we seem to be in luck. This, of course, you can see. So let me make the logarithms first. This is sort of the same with that. Everything exactly, even the indices. Now this also looks like it's the same with that. Everything the same, everything. So this cancels that. See? No, yeah, exactly. That's what we are doing. This minus that. So this cancels that and this cancels that. So the middle terms, gone. What have we got for the last one? Again, of course, we can see right away that this is plus. It will be just what we are looking for, by the way. T lambda mu nu, and we have established that this does not commute in general for tensors. The covariant derivatives doesn't commute in general for tensors, and that is what we have. So very quickly, we unlock already. Of course, we already know what the result for this should be, and this was what we found over here. The only thing now we can see is that in this case, this, by the way, you can see when I have lambda here, the lambda occupies this position. when I have nu k, k nu, for the first order nu k, the nu k is what takes over here. Then I choose whatever dummy index I like to represent that. So in this case, just for the sake, well, I can write this first, lambda mu. But what this bracket is supposed to give me is some r. We have to say this is some r mu on top, like we said. And I will have to choose whatever dummy index. So for the sake of argument, well, let me just take it to be b, beta. It has to be in this order, nu kappa. And then V, of course, beta. That's what I've got here. This is it. So at this point in time, again, it is still going to be plus some T lambda mu K minus T lambda mu K nu multiplying V mu. Well, however, remember we did show something, and that it was from this expression we obtained this already. This, by the way. So what can I do over there? I can simply, in place of this difference, replace it with r. And what would that be? R lambda, I'm guessing beta nu k, and this is going to be z beta. Exactly. So this is what I have. So very quickly, as I move on, you can see already from what we have, especially from the right hand side. Yeah. So let me just write that here on top. So what I've got is R, but remember what Z is. Z itself is that. This is what Z is. So in that order, lambda, beta, nu, kappa. Then instead of just Z beta, I remember then, of course, that the beta will take this position. So I can have it to be Z mu, V mu, T, but then beta, and then mu here. That is what Z beta will represent. Of course, that's what I have. Now, there is something. Since I have V mu here, beta over here is a dummy index. Yeah, that's what it is. Beta over here is a dummy index. But so also is mu. So I intend on this particular term, on this one alone, to perform an interchange between mu and beta. So I will say that this is the same thing as T lambda, but down there becomes a beta, and R, the mu also becomes a beta. Then the beta over there becomes a mu, and then nu kappa left alone, and then V beta that was there over there becomes V mu. And of course, this is going to be plus. Again, what we have over there is T lambda mu and K, yes, minus T lambda mu, but then kappa that, and then the whole thing is multiplied by V mu. Yeah. So what am I seeing over here? Now what I can try to do now is to combine these two together. For instance, this case here, I can write this both as, well, yeah. So that would be fine. I can say, for instance, here, let me just use a block bracket. So this is going to give me that. And in there, so I'm trying to factor V mu, which is common to both. This is T beta, this is mu, this is R lambda, B, nu kappa. When this comes over, it's going to take a minus. Of course, this is lambda, this is beta, this is R, beta, this is mu, nu kappa. And all this has V mu common to them. Of course, when this comes over also, I'm going to have there in the bracket, minus T lambda. Okay, this should be kappa, mu. Yes, and remember I've been all this while keeping all this. So this should be 0. Yeah. When I pull this to this side, it takes a minus sign, these two, and they all have V mu, multiplying them. This also coming out takes a minus sign, it also has a V mu. Of course, for any arbitrary V mu, everything here will have to be 0. And of course, if I write it in the way that I'm expecting, or that I want to show, since this is what I intend to do, this minus this lambda, mu, kappa nu. And this should give me then T beta that lambda beta nu kappa minus T lambda beta r beta nu kappa nu kappa. And of course, I guess this is what we have. And looking at this expression, just like we stated right from the beginning, does it have the feature we're talking about? Seeing that beta that was here moves over and the lambda that was here comes over. The beta that was here moves over, of course, and the mu goes over. So indeed, we have shown the measure or the main expression or the relation we said we wanted to show at this point. Okay, so now just to summarize, is also true, of course, we just use a mixed tensor here for a covariant index or covariant in two indices. We can also show that this is true. And so in general also it could be shown, this result was due to Ricci himself, it could be shown that this minus that, looking at an object like this, a P-rank tensor, of course going through the same derivative, covariant derivatives twice interchange LK gives us that result. So by the same trick, I'm guessing in this case, if you want to use a totally covariant index, well, it all depends. I decided to use this result for I think you may have to use this one in order to show for this particular result. In this case, I use such an expression as this. I'm guessing this time around, maybe you should try. I might be wrong, but I'm just going to suggest what I think anyway. This is going to be V lambda will then be equal to V sub mu. And then this is going to be T mu on top. Okay, so I'm guessing my lambda should be down. Okay, fine. I think so. If you were to use that object, but instead of using this expression like I tried to use initially, so let me just sketch this out. You may decide to do something like V sub mu. Okay, so I guess that will show up. This is nu and k, and of course minus the same V sub mu, but then k and nu. This should give us minus, this is going to be Z sub sigma, and that is going to be R sigma on top. And what I've got is mu nu k down, mu nu k. So of course, so of course you just remember when you're writing Z sub mu, it also simply means that Z sub mu will be equal to some V sub alpha say T alpha, but just make sure that the mu is down here. Yes. So if you have to use this, I believe you should end up with something like that for covariant indices. So at this point, I think it's fair. I mentioned the book again by Shum series, Tensor Analysis Shum series by David C.K. Yeah, David C.K. It's a very good book, especially for any beginner in tensor analysis. So like I've said before, so I've mentioned this one, and I think I particularly personally have benefited from the book. So it's only fair I mention these books as I go by. Thank you so much, and hopefully when we meet again, we shall learn more on tensor analysis and every introductory basics to general theory of relativity.